Welcome to Math 1314, Finite Mathematics. Barnett is our author. We will always refer to Barnett, and sorry Ziegler and Bilene, we're just going to say Barnett. Functions and Graphs, Chapter 2, and Section 1 is about functions. This is the first chapter, Objectives. The student will be able to do point-by-point plotting of equations in two variables. The student will be able to give and apply the definition of a function. So definitions, those are important. The student will be able to identify and define domain and range of a function. Function notation, the student will be able to use. And applications are always big in mathematics for business and the social science. Graphing an equation. Point-by-point plotting. Here's an equation. Y equals x squared minus 2. And we're just going to get a bunch of points, right? The way we do this, the way we have always done it since pre-algebra, is always to start here with x, make up values of x, and low integers near 0 have always been the usual suspects. And then the values of y will come out of the function. So of course we're going to take -3 here and throw them into here for x, and square -3, add 2. Okay, there's a mistake right here. This is supposed to be plus. And we come out with 11, so we're going to get a point -3, 11 on the graph. And put -2 in there. Look at this math, it's wrong. That's 4 plus 4, which should be 2 plus 2, which, oh wait a second, that is right. What's wrong is this one. If you put -1 in the function, square and add 2, and that's 1 plus 2, which are 3. So along with the points -3, 11, and -2, 6, there's a point -1, 3, and the others. So here's your point -3, 11 from the table. And on the graph, well, it's going to be across to the left 3 and up 11, right? So -1, -2, -3, and up 11. Up 2, 4, 6, 8, 10, 11. And there's the point -3, 11 on the graph. And we have all the other points. Of course, that wasn't right. We have -1, 3 on the graph. -1, 3. And so -1, 3. There it is. Plot all the points, draw the curve. So functions. That was a function that we just saw. Idea of a function is this: correspondence between two sets D and R such that to each element of the first set D there corresponds one and only one. That's the important part of this definition. One and only one element of a second set, R, which of course is the set of y values. But this one and only one, sometimes we say exactly one. So for every input there's exactly one output. So what you see there in green is probably a more useful definition of function. Then we have domain and range. The first set D is called the domain, second set R is called the range. And we have an example having to do with pizza. There's a set D, which is the sizes of the pizzas, 10 inches, 16 inches, and then you've got your range elements, the costs of the pizza, C, which we might have used the letter Y for that, $9 and $12 respectively. So the domain is the set of x values and the range is the set of y values. The domain is the set of x values which are allowed. Sometimes we say permissible. Well, what isn't allowed? Well, these are the two domain issues. The two domain issues. 0 in a denominator, negative under an even root. Any x value which does one of those things isn't allowed. And sometimes we use an arrow diagram or a map to indicate a function. And so you've got a domain D with the sizes of the pizzas, 10, 12, and 16. And then the range elements are the prices, $9, $10, and $12 respectively. And the arrows, show the outputs for the functions, the inputs of which are those three sizes of the pizza. Functions specified by equations. We're just going to take the x's and the y's, right, and let them produce ordered pairs. The graph of such a function is just the graph of the specifying equation. One output for each input. If we get more than one output for a given input, we don't have a function. Well, what about this? Y equals x squared minus 2. Do we have a function? Well, let us see. Let's see what happens when we take would-be x values and run them through the old function machine. For example, x equals negative 2. Throw it into the machine. This, of course, is the square the input and subtract 2 machine. So we're going to do that with negative 2. We're going to square it and be sure to include the parentheses. Come back. Be sure to include the parentheses when you're inputting values. 4 minus 2 are 2. So as always happens with the old function machine, we get exactly one output, which is 2. And so the point negative 2, 2 is on the graph, right? This was the x that we put in there, and this is the y that came out. Do we have the graph of a function here? Well, I don't think so, because these are the x values, right? That's the x-axis. Here's an x value for which there are two different y values. And so that can't happen for a function. But that's never going to happen over here, because any vertical line, no matter where you draw it, right? We could have drawn it over here, or over here, or over here, or way over here. But for the x value, there's only one y value that's going to happen. And so we do have the graph of a function. Of course, you recognize the vertical line test. And here's the statement of it. An equation specifies a function if each vertical line in the coordinate system passes through at most one point on the graph of the equation. Okay? At most one. Okay? So if you have two or more, not a function. Not. Following notation is used to describe functions f of x. Okay, it's not f times x, right? It's f of x. Keyword there. Of. So we could say f of x equals x squared minus 2. Okay, so this is just saying, the output when the input is x, and the output is a y, but we might like to use the letter f, right? Because we might have multiple functions, and on the calculator, it's going to say y1, y2, y3. And if we're using function notation, we can call them f, g, and h. Because, if you've got 3 students, it's better to call them Frank, Gary, and Harry than it is y1, student 1, student 2, and student 3. So here's a function. What does f of negative 3 mean? Well, we're going to replace x with negative 3 wherever we see x. So negative 3, replace x with negative 3. Don't forget the parentheses. And evaluate the expression. So 9 plus 2, that's 11. That means the point, negative 3, 11, is on the graph of a function. Okay? So f of negative 3 really means what is y? Because y is just f of x, right? Always. Y is f of x. What is y when x is negative 3? That's what we're finding when we get f of negative. So here's an example. Here's a function, f of x. Okay, it happens to be a square rooting function. Square root of 3x minus 2. Well, what is f of 2? Well, plug it in. Then we're going to multiply by 3, then subtract 2, according to PEMDAS, then take a square root. So 6 minus 2 are 4, the square root of which are 2. What is f of a? F of a, well, that's just kind of like this f of x over here. It's just that we're going to have kind of like this f of x. So we're going to have just a different letter, a instead of x. So square root 3a minus 2. What is f of x? What is f of 6 plus h? Well, f of anything is multiply that thing by 3, subtract 2 from the result, and then take a square root. We'll just do that with the binomial 6 plus h. So multiply all that by 3, subtract 2. Now, with the parentheses, of course, we're going to have to distribute 3. So 18 plus 3h minus 2. But then these two things here can and should be combined to make 16. This one, of course, is not going to be like with the other two things. So 16 plus 3h, it is not 19h, so it's square root of 16 plus 3h, and that's f of 6 plus h. We were given, right? The 3x minus 2, that is the radicand. We set the radicand greater than or equal to 0. That's always the way we do the domain of a square root function problem. Okay. And so that implies, right, if we add 2 to both sides, make our little scale here, add 2, 3x greater than or equal to 2, divide both sides by 3, and x is greater than or equal to 2/3. And so in interval notation, our domain is the closed interval, right? Because we're talking about all the numbers that are greater than or equal to 2/3. Okay, so everything at or to the right of 2/3. Okay, so 2/3. Everything at or to the right of 2/3. So, hence our interval notation. Find the domain of this function. Okay, well, set the radicand 1/2 x minus 4. That's the radicand. Set the radicand greater than or equal to 0. That's how we always do it. Radicand greater than or equal to 0. And we're going to get this domain. Set the radicand greater than or equal to 0. We're going to add 4 to both sides. Okay, this is just algebra. 1/2 x greater than or equal to 4. Multiply both sides by the reciprocal. 2 over 1, or just 2. X greater than or equal to 8. So closed interval, 8 to infinity, or in set builder notation, the set of all real numbers x such that x is greater than or equal to 8. Domain. Well, here we've got another domain issue, right? We had two domain issues. 0 in a denominator, negative under an even root. Well, we had negative under an even root, but this is the 0 in the denominator domain issue. And so we're going to kick out of the domain any x value such that we divide by 0, right? Because we're not allowed to divide by 0. That whole thing, you know, if we make 0 out of that whole thing, that's no good, because you can't divide by 0. Okay, so we're going to set the denominator not equal to 0. So 3x minus 5, which is the denominator, not equal to 0, which is to say that 3x can't be 5. That is, x can't be 5/3. So the domain is going to be anything except 5/3. Set of all x such that x is not equal to 5/3. 5x. So my bad. P of x equals 1000 minus 5x, where x represents the number of items and P of x represents the price of an item. Okay, so you're going to have a certain demand, a certain number of units demanded to be produced and sold, and a certain price that goes with that. Determine the revenue function and find the revenue generated. So two things that they want, an A and a B. Okay, revenue function, revenue. Okay, we have to think about that, what revenue is, and find, once you have a revenue function, find the amount of revenue generated if 50 items are sold. So if x is 50, then what happens? Okay, so there's our price function up here, and we have to think about what revenue is. Revenue is all the money that comes in sales, which is price times quantity. Now, they have here R of x equals P of x times x. And so what we have really is a formula for revenue that you have to remember as a business major or someone taking a math for business class. R equals P x. Okay, it's not complicated, but you do have to memorize that formula. So here it is, px. And price, well, that we got that right out of the price function on the previous slide. So P, that's your px right there, px. And so gonna do a little bit of erasing here. Okay. Won't go away. Okay. Anyway. Go away. It's not going away. Okay, well, let's simplify this function if we want. You know, we could say, well, that's negative 5x squared plus 1000x when 50 items are sold. What's the revenue? Well, we'll plug it in. Okay, so R of 50 is 1000 minus 50. So we're putting that 50 right in there and in there, times 50 times 50. Okay, which is 1,000 minus 250 times 50, which is 700. Break even and profit loss analysis. Okay, so there are costs and there are revenues. Okay, and it's not good if your revenues are less than your costs. You will take a loss. But if your revenues are greater than your costs, you will make a profit. Well, let's talk about the cost part of it. There are fixed costs like rent that you have to pay, and variable costs like labor you have to pay per hour. They are dependent on the number of items produced. So fixed cost plus variable cost X. Now, of course, we recognize in this the form y equals b plus mx, or mx plus b, where variable cost rate would be the m and fixed cost would be the b. X is the number of items produced, always in our business applications, right? So that's another thing we want to remember, because that's always true. And that's as true as that circle that I just produced is ugly. Well, we can have a price demand function, or just a demand function, usually determined by financial departments. They say, well, they relate demand and price by some geek doing stats in their financial department. They play an important role in profit loss analysis. Price equals fixed component minus variable component X. X is the number of items that can be sold at P dollars per item. Revenue function, R equals XP. Okay, R equals XP. Number of items produced, number of items produced and sold, times the price per item. Now, this is the price, that's P right there, and you don't really have to remember all of this. Just remember this: profit equals revenue minus cost. So here's the big thing right here. Profit equals revenue minus cost. And if you remember that, and you remember that R right there equals XP. So here's an example. Company manufactures notebook computers. Its manufacturing research department has determined that the data are modeled by the price demand function. So price and production are related by this equation. When X is in the interval 1 to 25 in thousands. So when you produce between 1,000 and 25,000 units, price and production can be related in this way. What is the company's revenue function? And what's the domain? They want the revenue function, revenue function. So that's going to be R of X, right? They want the revenue function. That's one thing you have to do, is produce that. And then you have to produce the domain of that revenue function. Okay, well, R equals px, or xp, and there's a price function that was given in the problem. We can simplify it or distribute the x and get this expression here of the revenue function. And so that's part of what they wanted, right? So we'll just box that. That's an answer. That's revenue function. And then they say domain. Well, it's still going to be the same. Financial department for the company in the preceding problem has established that the following, so here you got, the same geeks upstairs, they're, doing work. And they came up with this way of relating cost and units in thousands. Apparently it's a linear function. Following cost function for producing and selling X thousand notebook computers. So that's a cost function. Write a profit function for producing and selling X thousand notebook computers. Indicate the domain. So again, two things. A, write a profit function, and B, indicate the domain. You've got two imperative verbs here, write and indicate. So two things you have to do this problem successfully. Of course, profit, we know what that is. Profit is revenue minus cost. We're going to have a negative 500x, which together with this 2000x is going to make 1500x. There's also a negative 60x squared there. Maybe seeing this negative as a lead coefficient, we are starting to imagine a downward opening parabola. And there's our negative 4,000. Domain of this function. Okay, so there's a profit function. Okay, so we just simplified R minus C. So we have written a profit function. And there it is. So that's the answer to the first thing that we had to do. It's minus. Clean this up a little bit. Okay, so there's the profit function. That's the answer to part A. Part B, find the domain, indicate a domain. Okay. Domain of this function is the same as the demand of the original price demand function. X is between 1 and 25 in thousands. So that's why it starts here at 1. It really should, let's see, that looks like 5, 10, 15, 20, 25. So not exactly to scale here, but here's a graph of that function, and we see the values on the y-axis here. It goes up past 5,000, it looks like. So we get a graph, but we're just kind of interested in the domain, which goes from 1 to 25.